In this video, we are going to have if K is an extension of F and A belongs to K is algebraic over F, then F of A is a finite extension of F and vice versa. That is, whenever F of A is a finite extension of F, then A belonging to K is algebraic over F. So to prove this theorem, we need to have two results. So we'll first establish them first, and then come to the proof of this theorem. The first result states that if the mapping psi from fx to f of a defined by h of x psi is equal to h of a, then this psi is a ring homomorphism. It is defined like this. Any element here is h of x, say, the psi takes that element to h of a. Being defined by S, we will prove that this psi is a well-defined psi is well-defined so that it becomes a function. Once we prove that this is a ring homomorphism, we can call it as evaluation homomorphism. So to prove that it is well-defined, two elements in the domain are to be considered equal. Then obviously h of a equals g of a. So this is nothing but the image of h of x under psi, and this is image of g of x under psi. So that proves your well-definedness. Then to prove that it's a ring homomorphism, we have to consider h of x plus g of x of psi is h of x psi plus g of x, image of g of x under psi. So in the same way, under multiplication, we have to establish this. So if you consider the first one, this is a polynomial, this is another polynomial, sum of two polynomials, again polynomial, name it as f of x. So that h of a plus g of a will be f of a. Now if you consider LHS of 1, this we have taken as f of x. So the whole lot will now become image of f of x under psi. But it is evaluation homomorphism, therefore it is f of a. But f of a from here is nothing but this, and which is nothing but image of h of x under psi plus image of g of x under psi. So that gives the RHS of the first subdivision. In the same way for the LHS, if you take the product to be, say, some polynomial r of x, then h of a into g of a will be r of a. So similar procedure, if you consider the LHS, it is h of x into g of x, image of that under psi. So this bracket should have come here, not this. So this is r of x, image of r of x under psi, which is r of a. But r of a is nothing but this. So h of a into g of a, which is nothing but the product of image of h of x under psi and g of x under psi. So that proves the second subdivision, and therefore psi is a ring homomorphism. Then the second result, we need to prove this collection, which is a vector space, is an n-dimensional vector space. So what is it? So if g of x is a polynomial of degree n over f, and v is the ideal generated by g of x in fx, then fx mod v, which consists of elements of this form, is an n-dimensional vector space. So what is given to us, we'll write fx being Euclidean ring, any ideal is a principal ideal. So here we have considered v, which is generated by g of x. So v is an ideal, and the degree of g of x is given to be n. Now, in order to make this collection to be a vector space, addition and scalar multiplication, those two operations are to be defined. So addition is defined in this way, and multiplication. And we have been writing, even in the case of quotient space in vector space in UG, you would have written elements in this way, where V range over capital V. So under addition being this vector space being when you consider the elements over here, it's a coset. So whether you write W plus V or V plus W, it is going to be the same. So here, if you write f of x plus v, nothing wrong, you can write. But if you stick on to this notation throughout, you will have to use only the same notation. So fx mod v will be a vector space under these two operations. So that part is not given explicitly here, it can be easily proved. So we just assume that fx mod v can be easily proved to be a vector space over F. Now, having got that to be a vector space, we should try to check whether it is finite dimensional and find a basis so that its dimension is explicitly known. So we consider this collection S, which is the set of all elements v plus 1, v plus x, and so on, v plus x power n minus 1. We claim that this is a basis for our fx mod v. So for that, we have to show that S is linearly independent and S spans this. So to show that it is linearly independent, we have to consider the linear combination, equate that to the zero element of this. What is the zero element of this? It is V. So that is why you are writing here V. The linear combination you have considered and this. When you simplify this using the scalar multiplication and addition, you have this is by scalar multiplication. The next step is by addition. So this is what you get. And whenever you have this one should not come. Whenever you have this result is also established both in group theory as well as in vector spaces. AH equals H if and only if A belongs to H. And the same way in the case of addition, if you have V plus W is equal to W, then you must have V belonging to W. The same concept in vector space also you have. So this element should be a member of capital V, and capital V is generated by g of x. So this element can be written as h of x into g of x. Now here what we notice is if h of x is not equal to 0, then this will be of degree n, and this would be of degree, this will be of degree minimum n, so greater than or equal to n, and here the degree is n minus 1. So you cannot have one side with n minus 1 degree, the other side having n degree n. So what we can do is we can have only this h of x to be 0. Right, so if h of x is 0, this becomes like this, alpha naught plus alpha 1x and so on, alpha n minus 1x power n minus 1, 0. And 0 being rewritten this way, equating the coefficients of like powers, we get each scalar to be 0. So the linear combination equated to 0 element in fx mod v implies each scalar to be 0, and therefore S is linearly independent. Next we have to show that S spans v fx mod v. So for that we consider an arbitrary element, say v plus f of x in fx mod v. Now that you have got two members, one is f of x and g of x, fx being a Euclidean ring, you can use Euclidean algorithm, which in this case is called division algorithm, is true. So we apply division algorithm to f of x and g of x. So applying that, there exist polynomials h of x and r of x such that f of x is equal to h of x into g of x plus r of x. Here what we can mention about r of x is it is either 0 or degree of r of x is less than degree of g of x. Now here we notice one thing, when we consider v plus f of x, naturally f of x should not belong to v. Suppose it belongs to v, say, then what will happen? The whole lot will become just v, and v is the 0 element in fx mod v. The 0 element can always be written as the linear combination of any non-empty subset of fx, of the given vector space. So that in that case it is very obvious. So when you have this condition, then it is automatic that that particular element what you have considered, not particular arbitrary element, will be linear combination of the base, linear combination of the elements of S. So we are interested only in the second one in the category. So you consider v plus f of x, and that is v plus h of x into g of x plus r of x. From here we have this, and here g of x being a member of v, it will be absorbed by v. So you have v plus r of x, But what is R of x? It's of degree less than g of x. So you take it as say sum, n minus 1th degree polynomial. So you have this, and using and the operations addition, scalar multiplication, you have this step, addition actually, and here scalar multiplication, you have this. So you have this arbitrary element of in fx mod b to be a linear combination of the elements of S, and therefore S spans fx mod b. So number of elements being n, we conclude that fx mod b is of dimension n. So now we'll give the proof of this. So even here we need to have certain claims and then only give the main proof. You consider A to be algebraic. The definition of algebraic, we already mentioned that algebraic means it should satisfy some polynomial over here. Algebraic of degree n means it should satisfy minimal polynomial or irreducible polynomial of degree n. So here we just consider it to be just algebraic. Then also because it is algebraic, A satisfies a polynomial, say P of x of any degree, it will satisfy, in particular least degree that we consider, and that we take it as P of x. So which means P of A is 0, and degree of P of x is A satisfies a polynomial, say P of x we have said of least degree n. So degree of P of x is n, where n is the least positive integer. Now we want to show that this P of x is irreducible. This we have proved in the earlier video, that irreducible minimal polynomial will always imply the irreducible polynomial. Least degree we have mentioned, which means it's the minimal polynomial. It is minimal polynomial. So P of x is irreducible. We need to establish. Suppose it is reducible with degree of R of x less than degree of P of x, and the other one, degree of H of x less than degree of P of x. Now P of A is 0. You can apply psi on both sides. So it is P of A, H of A into R of A. And P of A being 0, you have this to be true. So this in turn implies H of A to be 0 or R of A to be 0. That is because f of A is a field. Every field is an integral domain, so you have this. Now if h of A is 0, then A satisfies the polynomial of degree less than the degree of P of x. So that is, you have assumed P of x to be the minimal polynomial, but you have got now another polynomial whose degree is less than the minimal polynomial satisfied by A. So that cannot be, that is not possible, and therefore our assumption that and this is reducible is wrong, so it should be irreducible. So on the second claim, we have we are defining psi from the same thing what we considered just now, second result. Fx to f of A defined this way, that's called evaluation homomorphism. Then once it is a homomorphism, you can talk about its kernel. Kernel of psi is all those elements whose image under psi is 0. So that is nothing but g of A, all those g of x for which g of A is 0. Now we will denote this kernel psi is always an ideal, so we will denote that as, say, some capital B. Now M is an ideal of fx generated by the irreducible polynomial P of x. So that is now we consider it is it is the see, you forget about the V which has come in the second result. You should not get confused between this V and that. So here we consider M to be an ideal of fx generated by the irreducible polynomial P of x. So M is generated by P of x, where P of x is irreducible. Then M is maximal. M should be maximal in fx. So you will have M contained in V contained in fx. M is an ideal generated by the irreducible polynomial. and B is this. But you have got between M and Fx 1B. How is it true? You have your M contained in B. This part, how it is true? You consider an element, say P of x itself. You consider P of x belonging to M, because M is generated by this. You can consider this, right? Once you have P of x belonging to M, and P of A also, because P of x is a minimal polynomial satisfied by A, you have P of A 0. But all those polynomials which vanish at A is a member of kernel. It's a member of kernel psi. It's a member of kernel psi, and kernel psi is taken as capital B. Kernel psi is capital B. So any element in M is now an element of B. So that is why you have M contained in B, contained in Fx, and because M is maximal, either these two should coincide or these two should coincide. Now M equals V if only holds. The reason is you have an element, say 1 in Fx, but that is not present in V. So we have so this the other one will not hold good. Only M equals V. So this in turn, because M is generated by P of x is irreducible P of x, and therefore it is maximal. So you have your V to be maximal. Now when you have Fx to be a commutative ring, and Fx mod V, of which V is maximal ideal, then you have this to be a field. Fx mod V will now be a field. Fx mod V is a field. So now we will claim now the image of f of x under psi is f of a. Obviously see, we need to prove that this is contained in this and this is contained in this. So this one contained in this is very obvious. So you have this one, that is what is stated here. So you have this. Now by first isomorphism theorem, when you have onto homomorphism with kernel this, then Fx mod V should be isomorphic to Fx psi. So now we will claim that Fx psi is f of a. So it's a field, and one more thing, that a equals xy belongs to Fx psi and alpha also. So Fx psi is a subfield of K containing both F and A. Since F of A is the smallest field of K containing F and A, the smallest must be contained in any other F of mod x under psi. It is contained in this. Now from 4 and 5, you have your Fx mods. Fx psi is f of A. Fx psi is f of A. So f of A is contained in f of A, I mean the image of f of x under psi. The reason is psi is a mapping between f of x and f of A. So this is contained in that Fx psi. So that is, which is contained in what? Fx psi is contained in f of A is very obvious. But what we have stated here is f of A is contained in this. That is because Fx psi is a field, and this is a this is also a field. F of A is also a field. This is the smallest, which contains both F and A, and that is any other. So you have, and this one, how does it come? That is also to be noted. That is what is explained here. So V is maximal means Fx mod y is a field, mod V is a field, and hence this is a field. So that is explained there. So both of them are fields, and one is contained in the other. So we must have equality. F of x psi is f of A. Now since Fx mod V is isomorphic to f of A, And fx mod b is an n-dimensional vector space over F. We have f of A to be an n-dimensional vector space over F. So fx mod b is isomorphic to this, and this we know to be n-dimensional, so you need to have f of A to be an n-dimensional. So mathematically this is how we represent degree of f of A over F is n. Hence f of A is a finite extension. Now for the converse part, we shall take f of A to be finite extension of F. Then degree of f of A over F is finite, and let it be equal to, say, n. Now this in turn implies that f of A is an n-dimensional vector space over F. Then the n plus 1 vectors, namely 1, A square and so on, A power n, these are more than n elements, n plus 1 elements rather, in f of A. The 1a and so on, A power n, are linearly dependent, and hence n plus 1 vectors they are. So which means that there exists scalars not all 0 such that the linear combination is 0. These scalars are from F. This in turn implies that A satisfies a non-zero polynomial over F, and so your A is algebraic. So that is the end of this theorem, which has preliminary results to be established. So as such, the proof of the theorem, depending on the time available, you can give the detailed proof of those two results. Otherwise, it must be definitely stated. So we have the definition: an element A in K is said to be algebraic of degree n if it satisfies a non-zero polynomial over F of degree n, but no non-zero polynomial of lower degree. Right? So then in that case you say that your f of A, see the converse part in that, we have assumed this to be an extension, f of A to be an extension. We need to establish that A is algebraic, which means A has to satisfy a polynomial. So this implies that it satisfies a non-zero polynomial. See, here we have mentioned that there exist scalars not all 0. This point is to be noted. This we will be recalling when we prove another result. So there we will have to recall this, because there the converse part will not be true. That is because of this constraint only. Right? So element algebraic of degree n means A satisfies a non-zero polynomial over F of degree n. It should be a minimal polynomial, but no non-zero polynomial of lower degree. So we will have this example: root 2 is algebraic of degree 2 because it satisfies this polynomial. See, if we are given, say, x square minus 4, say, then it's a polynomial over Q undoubtedly. There is no need to have an extension for this, because the roots of this polynomial are just plus or minus 2, which are very much available in this. So you can adjoin with this Q another element only if it is not present there. And on the degree, we can easily mention all that. Again, it will be said in the following videos, that how do you determine the degree of this is an extension, immediate extension, so simple extension. How do you say that the degree is 2? Now this root 2 satisfies a polynomial of least degree, namely 2 over Q. So you have that to be whatever degree of the polynomial is the degree means dimension in this case as a vector space. So you have that to be 2. So root 2 satisfies this polynomial and no other polynomial of lower degree than 2 over Q. Over, that word is very important. This is what the next theorem we will prove in the next video, that if A belonging to K is algebraic of degree n, then degree of f of A over f is finite. Here we will not have the converse part, because once you have the converse part, for which you will be assuming this, there is no problem. You will proceed in the same way only. But here we have said that there exist scalars not all 0. For A to be algebraic of degree n, exactly it should satisfy polynomial of degree n. Here the degree we cannot determine because we do not know which of the scalars are 0. Supposing I have alpha n to be 0, say. There exist scalars not all 0, we have said. So if alpha n becomes 0, then this A will satisfy a polynomial of degree n minus 1 only. Then you cannot call it as A is algebraic of degree n. So that is the reason why the reverse part will not be true in this case. If A is algebraic, what we had in the previous theorem, A is just algebraic, we never mentioned about the degree. Then f of A is finite extension. So one way, if this is asked, either this proof or that proof you can give. But when this is, for the converse part, this can only be true. You cannot have that to be true in this case. So this we will prove in the following video. Thank you.